quite as simple as the last one. As we go through the circuit, we start at the battery, we have to pass through the 5, we have to pass through the 10. So that means the 5 and the 10 are connected how?
Series.
Series. We get to a branch, so now we have a choice. We can pass through the 20 or the 10. So the 20 and this 10 are in parallel. Comes back together, 30. So we need to break this down until we can figure out the charge or potential on any one of them. We know that the 5, the 10, the combination of the 20 and the 10, and then this 30 are all in series with each other. So that means whatever voltage the 5 has, plus whatever the voltage the 10 has, plus whatever voltage either one of these has, plus whatever voltage the 30 has to add up to be 20. So you start combining things that you know are how they're connected. So for example, the 5 and the 10 are connected in series. So yes, we'll make you happy this time. We'll derive the easy one. If you get a common denominator, so C2 over C2, C1, C1 over C2, C1, that's going to be C2 plus C1 over the combo of C2, C1. We flip it over, C equivalent, C2, C1 over C2 plus C1. Same thing as what we were doing before. So we have the 5 and the 10, they're in series. If we call C1 5 and C2 10, we're going to have 10 microfarads times 5 microfarads over 10 plus 5. So 50 over 15. The bottom microfarads cancel with one of the top microfarads. So our units will be microfarads. Let's see, 5 into 15 is 3, 5 into 50 is 10. Oh, that's convenient. Same answer. 10/3 microfarads. That's the same thing as just taking the 1 over C equivalent is equal to 1 over 5 plus 1 over 10. Same answer. So we've combined the 5 and the 10 in series. Any questions on how we came up with the equivalent capacitance with the 5 and the 10 in series? Okay. Coming down, we know this 20 and this 10 are in parallel, so we're going to treat them as one capacitor. Simply enough, in parallel, you simply need to add them, so their equivalent capacitance would be 30 microfarads. Brings us back to this final 30. And our battery's still 20 volts. Now we still don't have enough information to know the charge or voltage on each of these. So we need to simplify again. How are these 3 capacitors connected? In series. If we if we start at the battery and work our way around the circuit, we have to pass through all 3 capacitors. So all 3 are in series. So we're going to find one equivalent capacitance for the whole thing. So we have 1 over C equivalent will be 1 over 10/3, which is the same thing as 3 over 10, plus 1 over 30, plus 1 over 30. Let's get a common denominator. 9, 10, 11. So C equivalent is 30 11ths. microfarads. I don't like that fraction because 11's not going to simplify nicely, so I'm going to just get a decimal place. Now this is a rounded number, but as long as we keep a few decimal places, we'll be good. Okay, questions on coming up with the equivalent capacitance of the circuit? Yes?
On the one on the right side, how do you get the third? No, the middle one, right there, yeah.
The 20 and the 10 were in parallel.
All right.
In parallel, you simply add them together.
Right, okay.
So parallel is easy. Just add them all. So 20 plus 10 got 30.
You're essentially increasing the size of the plate on each side.
Exactly. It's equivalent to increasing the area. Well, we know the total voltage supplied to the circuit. We know the equivalent capacitance. So we can easily find the total charge. Total charge is the equivalent capacitance times the total voltage. So 2.73 microfarads times our 20 volts (54.6 microcoulombs). So that's the total charge that the battery forces to flow, to move in the circuit. I don't trust myself, so I'm going to double check. Okay, now we have to work our way backwards. The total charge, that's what the battery pumps out and forces to move. That means that total charge accumulates here. It'll move through here and accumulate here. Gotta keep the units right. Moves through and also accumulates here. So once charge is moving in one part of the circuit, it's moving everywhere in the circuit. Since these are in series, they have to have the same charge. Well, we know the capacitance, we know the charge. So delta V will be the charge over the capacitance. So 54.6 divided by 10/3. Delta V for this top capacitor will be 16.38 volts. Charge divided by capacitance, 54.6 divided by 30. And this is the same charge divided by same capacitance, 1.82 volts. Now the 3 should add up to be 20. They don't add up to be exactly 20 just because we're starting with a rounded number here, which this is rounded as well. So it'll be slightly off of 20 when we actually add them up because of our rounding. Looking back here, this 30 microfarad is the same as this bottom one, so we're good. We're done as far as this bottom capacitor goes. We know its charge. We know its voltage. But this 30 microfarad capacitor on the side was representing the combination of that 20 and that 10 microfarad capacitor. Out of this information here, what can we take back to these individual capacitors?
Use the voltage, the drops across both.
Right, the voltage. Both of them, since they're in parallel, they have to have that voltage drop, the 1.82 volts.
Can you also distribute the charge evenly between the two? Like you could say,
The charge will not distribute evenly.
well, not even, I'm sorry, I mean 20 over 30 times the total charge for the 20 microfarad. 10 over 30 of the total charge for the 10 microfarad.
Yeah. So the 54.6 is shared between them. We can easily find the charge, capacitance times delta V. So 20 times the 1.82. Well, I give up. Whoops. So Q is equal to C delta V. We know their individual capacitances. We know their voltage drops, so we can easily find their charges. They add up to be the 54.6. So we're good with those. Now we have to figure out the last two. The 5 and the 10 together were represented as this 10⁻³ microfarad capacitor. So out of this information that we know for the 10⁻³ microfarad capacitor, what can we take back to each of those? Charge. They're in series. Whatever total charge their equivalent has is the total charge each of them have individually. So each of them has the 54.6 microcoulombs of charge. Using our little nifty equation, once again, delta V is Q over C. So 54.6 divided by 5, 10.92 volts. 54.6 divided by 10, 5.46 volts. So we know the charge, the potential difference for each capacitor. It would be very easy to now find the energy for each capacitor. 1/2 C delta V squared. We know all their capacitances, we know all their delta V's. We could easily find their energies.